I want you to imagine a situation. Imagine you are driving a car and currently standing at a red light. There are a lot of cars behind you. The queue is growing. However, you take a look at the next road and you see that there are no cars there, but their light is green. So you wait and wait, your light doesn't change. And eventually your light changes. But when it's time for you to move, you see that the next intersection is already crowded. There are a lot of cars. Because you were waiting for so long, the queue has already been developed. That is a problem for many fixed schedule traffic light systems. So it seems that traffic lights don't actually see the traffic. They don't understand what is going on. They are working with fixed schedules. And the question that I asked during this talk is whether traffic lights can learn to make better decisions to make the traffic flow better. I'm Victoria Hovsepian, a data scientist, and during this talk, I will answer the question using reinforcement learning and Sumo simulation environment using 6 Komitas Avenue intersections. So, as I've mentioned, most traffic lights do not really know traffic. They don't see what is going on, and they just follow a predefined schedule. What does predefined schedule mean? So imagine you have just 2 roads, like Komitas Vagashian intersection. You have 45 seconds for Komitas green. Then as soon as it ends, Vagashian gets 25 seconds of green, and then the cycle repeats on and on. So that cycle is the same whatever the traffic conditions really are. It doesn't matter. So whether it has been an accident there, whether the time of the day changes, it's rush hour or quiet time, the conditions are the same. So these pre-planned schedules work pretty good only in the cases where the traffic really mimics the designed it really mimics the traffic conditions that were used to define the system. In all other cases, it fails. And we have all noticed that during driving in Yerevan. But that is not that innocent because it costs time and money. It causes longer waiting, more idling, unnecessary fuel consumption, as well as inefficient intersection usage. However, there are some more systems besides fixed time signal systems. Actually, there are sensor-based systems that are Scoot as CATs, for example. They work as a rule-based approach. So the engineers design some rules for the traffic lights to understand what system, what phase to use now, and with what duration. However, this is quite limited because it's still designed by people. They are the ones writing rules, setting the thresholds, and it looks something like that. If you see that there are more than 40 cars in Komitas Road, then make it green. So this may work very good in just one intersection when our main goal is just to clear that one road very quickly. However, scaling becomes horrible. So it also becomes very hard to tune. Imagine writing rules for one intersection. Now imagine writing rules for more than 6 intersections that really need to talk to each other and understand what is going on in other intersections. Because if I try to make the traffic much easier in one intersection, then it will just go and make a queue in the next one. So we need some approach that learns, that is quite dynamic and understands what to do from the certain situation. That is where the reinforcement learning comes into the game. So reinforcement learning may sound pretty difficult. However, the foundations are quite easy to understand. It is a loop between an agent and its environment. It has 4 more components. So the components are the environment, state, action, and reward. The environment is the world that the agent operates in. In this case, that environment is our Komitas Avenue with all its intersections that we are considering. However, since we are using a simulation here, our environment is a simulation. The state space, the state itself, is all the information that is available to the agent. For this case, that state information is actually the queue lengths, average waiting times, the green durations, and whatever the agent may consider important and informative for making the decision. Then we have an action. agent is the one doing an action. So it is the decision made by it. That decision is a conclusion of previous actions and rewards. So what is the reward? It is a score showing how good the decision is. In most of the RL problems, reward is the most important part, because this is how you non-verbally tell the agent what do you want from it. This is just a formula explaining the higher value of which indicates a better action, lower value is some kind of a penalty. And this is how you need to teach the agent. And we have the policy, that is the rule that the agent uses to choose an action based on the current state. And our main goal is to learn a policy that gives highest total reward. So let's understand how reinforcement learning works from a simple example. Let's take Frozen Lake example. This is actually the game that I used to play a lot when I was little. So we just have 4x4 grid cells. A grid composed of 4x4 cells. The agent is our elf here. Here is our agent. And here is the goal that we want to reach. It must perform different actions. It can go up, down, right, and left. These are 4 discrete actions. And it must avoid all these holes, because when falling into the hole, it will go back to its initial state and the game will restart. So what is the problem here? Why can't it just do it? Because initially, imagine the elf is blind. It doesn't see anything. So it just doesn't know where the holes is, what will happen if it falls into a hole. So it doesn't know that, we know the rules of the game, it doesn't. So it just tries random movement. So it goes down, sees that everything is fine, tries going right. When it goes right, it receives a reward -1. So it's a penalty. It understands that it performs some bad action. So when appearing in this state for the next time, it won't go right. It will try other options. It will go up, go down, try to go left, whatever. And when going left, it will see that 0 reward comes. So what is the point of making that action at all? That is how the agent learns. It does random actions. It learns from it. So this small grid has only 16 states. It's very easy to literally just write values for each state action pair. From this to this is just -1. It's very easy. But when we talk about traffic, it becomes very difficult, because in fact that a real intersection has millions of possible states. So a simple table won't be able to hold that. It will be just an infinite table, because we have continuous state values. So now let's see how the RL works on the Sumo simulation environment. Here you can see the cars moving, the traffic lights colors changing, and this is actually done in Sumo, simulation of urban mobility, which is considered a microscopic environment. Microscopic in this sense means that each car is modeled separately. So each one has its own route, its own speed, and it is just acting separate from each other. So here you can see all of the 6 intersections that I've modeled during this project, during attempts to find an answer to this question. You can see the lights changing. So the road is crowded, so the light changes. Now let's continue and understand our problem. So we have understood what RL is basically, and now we need to understand how it can be used with our specific network. I have used 6 intersections that are Komitas, Gulbenkian, Vaghashian, Papazian, Vratsakan, Gripaev, and Tigranian. Here, all the data is gathered from OpenStreetMap, so the network itself is real. However, it had a lot of flaws. One of the major parts that are very important is that when directly importing the map from OpenStreetMap, it has this random small traffic lights generated in it, because it treats each direction, each possible movement as a separate traffic light. which is the worst possible option to go with, because it will create more than 20, like more than 10 traffic lights, separate agents for just one intersection. That is, in fact, its logic corresponds with just one in a traffic light that controls different phases, not different movements. We'll understand what the phases are very shortly. So I used 3 traffic levels here: off-peak, rush hour, and heavy stress. They just differ by volume, number of cars. Now let's understand the 3 main factors: state, action, and reward of reinforcement learning. Let's start from state and action. Let's take a look at drones, how drones or robots have their states and action defined, and whether they are continuous or discrete. Because in fact, it decides a lot. This is where the choice of algorithm comes from. Drones have position, speed, direction, all of these. This is the information they need to make a decision, and all of these are continuous variables. Their action is movement and joint control, which is also continuous. So it will be very difficult. It should be a complicated model for that. Financial markets have prices and signals state. They are continuous. However, their actions, we just have 3 actions: buy, hold, and sell, which are discrete, so much easier to model in this case. And finally, our traffic signals. The states are cues and timings, and whatever we decide that is important for the model. And the action is choose a phase or extend the current one, which was my decision to set as discrete. But many papers still consider the action space to be a continuous. So more models are available. Now about the state space and what it contains more in details. So it has phase and timing, cue pressure for each green phase, position in the cycle, local traffic, the pressure on the worst lane, total waiting time, and what is happening on the next intersections. So in order not to create a graph and trying to make the agents talk to each other, we are doing it indirectly. We are in each agent's state, we are giving information about its neighbors. For example, the previous and next intersection cue pressure, spillback pressure, their phase position. So if an agent sees that in front of it, the next intersection is pretty crowded, it is less likely to now send a road there, a whole queue there. And the actions are pretty simple. So you just extend, keep the current green for 5 more seconds, or choose another green phase, and change. And in this transition, a yellow light is generated in order to make the transition safer and according to all the rules and standards. Now let's see how the phases look like. The phase I've talked about, that the Komitas roads are open, is this phase. So upcoming and outcoming, all here are open, but no one can move in Vavarsian. However, when we see that actually the queue is pretty well cleared up, we just need to switch to Vavarsian. There is no need for us to keep this phase, to just log this and keep this, because it will just take more time. However, so our agent will decide to switch from phase 1 to phase 3 immediately, because it needs only Vavarsian open. And during this transition, a yellow phase will be generated by making this yellow. And the reward, which I consider the most important part of reinforcement learning. So first try, when trying to model this for the first time, I used local reward. I just told each agent to try to minimize its queues and average waiting times and whatever I considered important for that local intersection. However, it worked terribly. Every intersection became selfish. They were just trying to move their cars, however, creating a queue in the other intersections. That is why I added that information about the next intersection in the penalties, in the reward formula as well. So the reward formula consists of 2 parts, rewards and penalties. The rewards serve the movements. We reward the agent if it serves the movements with the most pressure, if it supports the flow of the whole corridor, cooperation between intersections. And we penalize the agent if it creates high pressure, so if an action is taken and then long queue appear, waiting time increases, and all other metrics go worse, it just something was off. So that action was not beneficial there. And ignoring a low traffic road is, which I call starvation, is also need to be penalized. Pushing cars into blocked road, changing too often, or holding green too long. So what model did I choose and why? Since we saw that our state space is continuous, we can't use a table. Just tabular approaches won't work because we'll have an infinite table. A neural network estimates the Q value instead of us just manually inserting them into the table. The actions are discrete, so there is no need to go for heavier continuous control methods. We can just use DQN, double QN. Normal DQN, however, tends to overestimate values. Double DQN fixes this. One network chooses the next action, another network estimates the action. And we have a sixth agent, as I've mentioned, one for each intersection. We can see that here are the results. The numbers here are in plus. This shows the improvements, but this means that these average numbers decreased. So it's not that good visualization. So we see that the average queue decreased, average trip duration for single intersection RL. This was Komitas-Velasyan intersection. And average waiting time decreased, and the most important improvement we have in max waiting time, we have 65% going down. And I've tried the same, like multi-intersection RL, and we have some improvements here, not as good as this one, but it is still performing better than the baseline. And the max waiting time decreased as well. I've also compared this with max pressure. I didn't want to use only one baseline, so I have used max pressure as a rule-based alternative that is always giving priority to the most heavy road. And here we can see that it worked better in rush hour and off-peak. This is average waiting time. But in stress test, max pressure works a little bit better, which was expected because when you have stress corridors, when every row is filled, opening the most heavy one will, of course, make the situation better. It has some limitations, even though the results are good. The traffic is generated by the model, not from real sensors or cameras or historical data. The simulation does not include some other factors like people crossing, outside crossings, bus stops, mixed driver behavior, so it is kind of idealistic, even though it has real map data. Each agent works on its own intersection, so corridors spillback can still happen even if we include that information in the reward and state. And we need to reward weights. Also, not only, as I've mentioned, all the data collection I did myself. I went to all of the intersection, gathered it on using pen and paper, and then I needed to also gathering the information about the next intersections, because if I don't do that, then they start acting randomly, intervening with my main Komitas avenue. So that's it. Thank you very much.
Thank you very much. By the way, great presentation about the simulations. It's always interesting, all related simulation. But I don't see the safety factor. Should we consider about safety? Because I believe it's important, right? And second question about I saw that in the limitation, I saw that not consider the bus stops. I believe bus stops might be public information, right? Why not consider about it?
Yes, that can be done. So I'll start from the second question. Bus stops can definitely be considered because we both know the schedule and their locations, but that's just what I didn't include in this project. It's the limitation of this project specifically. And the first one, I believe you asked about safety. So if you mean safety like causing accidents, That is also one of the limitations. So one of the limitations is people crossing outside and mixed driver behavior and so mixed driver behavior is one thing that may cause problems, but if you mean that some accidents may happen because it switches between the phases, the phases are designed in a way that they are perfectly, so it is not deciding to open these but leave this open. If it decides to open comitas, it will always close the Russian. So no car is coming from that part. No accident will happen. That is why I've decided to use phases as actions, not separate roads.
Thank you for presenting this presentation. The idea of this project is awesome. But I have one question, like, don't you think that having separate agents for every crossroad is too expensive in sight of like managing it and like hosting servers to hold all agents together? Because I don't know double DQN architecture, so I don't know if it is efficient, but don't you think that it will be a problem to host it?
So I believe that it will 100% be expensive to host this, but I believe that it will be more expensive to make a full centralized RL, that one agent for the whole comitas. It will be expensive in terms of RL weights, state space, and action space, which in fact may be worse than having several intersections.
Yeah, thank you so much for your talk. I wanted to ask like a connected question. So if, yeah, of course, it's really difficult to make one agent that can control all the intersections. And if we have more than 6 intersections, it's very difficult. But I wanted to ask if you are thinking about adding maybe some information stream where like all the agents can communicate and like synchronize what they're doing. So we still have like 6 agents. So like we have a separate agent for each intersection, but we add some channels so agents can talk to each other and maybe synchronize what they're doing. And maybe thanks to this, we can solve this problem that every agent is selfish. Did you consider these approaches, or maybe you have tested something like this?
Yes, so one part of it is already included in my state space and rewards. So I'm trying to give separate agents information about what is happening in the next intersections. But in terms of what actions they choose to do and if they want to inform that, it also can in some ways be included in the state space. But I don't think it will be much better than that. And yes, I believe that one thing that needs to be tried. So I've been thinking about it when doing this project. So instead of having one centralized approach, have the centralized agent, which still report each other's decisions or each other's values to each other. So one intersection can predict what other will do if he sends the cars, something like that. Yes. Thank you very much.